Now here in this part of the video I will introduce building blocks, the basic examples of operators that we're going to focus on. The first one is called the identity operator. Given a function, what this operator I is doing is nothing. That just spit out y. It's called identity operator. This operator E alpha is called evaluation operator. So if you do E alpha to this function, it spits out the constant function, not a number. So if I given a function, you evaluate that function at alpha, then it gives a number. But we interpret that as a constant function. Third operator I'd like to introduce is called this differential operator. This is something you learn in calculus. One variable, the very first course of the calculus, one variable calculus. Given a function, we consider the differential function, the derivative of the given function. So the space of function we're looking at so that we can do this operator is differentiable functions. The last of this basic operator we introduce here is the integral operator. Given a function y, we're just going to use this abbreviated notation, the integral symbol a. This is not the usual integral symbol. This is the symbol for as an operator. Given a function, we're going to consider this area function. I hope you recognize this as a function form where our main input is this upper limit of this definite integral. So given a function, we can consider this very specific definite integral. So we're calling this one not definite integral, but as an integral operator. Given a function, we create this new function using the definite integral. So these are the four things that we're going to use to capture the operator algebra of a one variable calculus. Now let me explain about this interaction, the algebra of these two operators. I just introduced as an identity operator. This operator does nothing to the given function, and D was a differential operator. Now what I just did it here, and we all know what these two operators are, and I symbolized it. The action that you do, the differential operator and nothing operator, it's symbolized. It's using the English letter D and I, as if these two things are numbers. But remember, this is a number, not a number. It's built on top of a space of functions, so it's quite abstract notion. But we use this English letter to turn this into an element, D plus I. So we just have to give a meaning to this one. D was an operator and I was an operator. Now D plus I, what kind of operator is it? So to give a meaning, you just have to explain how this one operates on function. Given a function y, what it does is that first you differentiate it and add the second operator, the result of a second operator, which is doing nothing to that function. So what this operator D plus I is, given a function, y prime plus y. Just like that f plus g, the sum of two functions is defined. So that's what it means, D plus I. So what we're doing here is that this abstract notion of operator is symbolized like this. As soon as we symbolize, we can create algebra to add and subtract and different stuff like that. In the function case, it has an interesting operator called the composition that it is not inherited from the basic for arithmetic operation. Few more notational thing. I, and we recognize this an identity operator. X squared is that it's a little abusive notation. X squared is really a number, but we accept that as a functional notation, x squared, the square function, the quadratic function. So when you look at this, so x squared is not the operator notation, this is a function notation. So I have to give a meaning to that. What it means is that if I give a function, identity function picks up the function input function itself and multiply the x squared to that given function. So here it's two operator written next to each other as if E alpha is a number and I is a number, and put it together. But these two are operators, and this is not really the multiplication. This is kind of composition of operators. So what this one is, as an operator, if we write this evaluation operator and identity operator right next to each other, what it does is that first y is the evaluation function. It's identity function, so that will become just y, like this. So that whole thing becomes just y, as if we're doing this composition of functions to a number. We're doing this composition of two operators to a function. So I will do the inside operator first, which will give you y, and then we do outside operator, the evaluation operator. So the evaluation operator spits out the constant function. So this operator will spit out constant function. And what it does really is that what this operator does to this function y is exactly the same as the evaluation operator. Remember, if there weren't I in there, and if you just apply the function y in there, you will get this one. That's the very definition of this evaluation operator. So we can conclude by looking at how this operator operates on arbitrary function is nothing but the same old operator in the evaluation operator. So if we symbolize this operator like this and try to explain the algebra between this one, and first I gave the meaning of when we write it as if it is a multiplication, but it's really the composition of operators, then it's the same as this, E alpha, as if this is the multiplicative identity 1. And you can argue easily that if L is whatever the operator, not just the evaluation operator, is differential operator, whatever the complicated operator we can imagine, if you go through identity operator and then do this operator L, and if you compare that with do that operator L and do this identity operator I, they end up at exactly the same. So as if after we symbolize, this I really works like multiplicative identity to the right or left. So this is another example. I played with this evaluation operator and differential operator. If I write down this symbol E alpha right next to D, what does that mean? The most natural thing is that you apply the function to that. So the first one is derivative. So you arrive at here. The derivative of y is denoted by y prime, and you evaluate. Then you get y prime alpha. I don't know, there's using that four operators I introduced, there's not much a better way to write this one than E alpha D. So that's pretty much it. That's the meaning of this E alpha D. But let's think about this D E alpha. So evaluate, then differentiate. So I want you to take a moment and think about what this really means. If you evaluate, this becomes a constant function, and differentiating that constant function, it will always result in the zero constant function. So these two things, if you write it right next to each other, these two symbols, as if they're multiplied to 0, while these two things is not multiplied to 0. So E alpha D and D E alpha is not the same thing. We've seen this type of non-commutativity in matrix algebra. So after we symbolize it, do not assume one operator written next to each other is the same as the operator written in swapped order. Right, one more example. The reason this E alpha, the evaluation operator, was introduced is to cover the following phenomena. This is integral operator, and this is differential operator. What's going to happen if I put these two things together? I want you to take a moment and think about what is the best description of these two operators written next to each other. Sometimes there's no way to really simplify it. This is as simple as it gets. But sometimes here you can make it a lot simpler. Let's think about it. I hope this came to your mind. Fundamental theorem of calculus. Given a function integrated through this definite integral and differentiated, it becomes the identity operator. Because the integrated and differentiating cancel each other, becomes identity operator. That's exactly the statement of the fundamental theorem of calculus. Now let's think about doing d first and integral later. You have to be careful. You really have to play with the function y and see what this one is going to end up in. Answer to that one is the integral identity operator minus this evaluation operator at a. So this is exactly why this evaluation operator is introduced here, to cover these two things. So let me explain in more detail with the function applied. So the first one is that if you apply the function to the integral first, you get this definite integral part, and differentiating this area function is exactly just inside function y, and that's the very statement of a fundamental theorem of calculus. So this operator algebra, after you symbolize it, we have this kind of inverse factor d and integral kind of multiplicative inverse to each other, and gives you this I. However, if you multiply backward like this, you don't exactly get just I, but you have this extra factors. Again, you can see the non-commutativity of this differential algebra, the operator algebra. So if you do to that part differential operator first and integral operator, then you get this. First, this inside part becomes y prime, the derivative, and the meaning of this integral operator to that one is really this function. As you can see, the antiderivative of this integrand inside here is yx. That is a unantiderivative, and you can use that and to evaluate this definite interval. That's also part of the fundamental theorem of calculus. So yx minus ya. So this is a function y, so that's why there is this identity and there is this evaluating function. So as an operator algebra term, and these two things, if you put it in this order, it becomes identity. If you in reversed order, then it becomes I minus evaluation operator A. So I moved things around a little bit. Now I want you to look at it here, and we have an interesting statement that is now called the fundamental theorem of calculus. Is that differential operator and integral operator, if they're juxtaposed in this order as an operator algebra, it becomes identity operator, and if you put it in this order, this identity operator minus this evaluation operator. So fundamental theorem of calculus can be summarized nicely like this. Here's another example. D is a differential operator, and sine x is multiplied to that. The meaning of this one, of course, the first differentiate and multiply to this function that looks like an operator. So that's exactly what this means, and I'm claiming that this is pretty much as simple as it gets. But what if we swap the order? For example, like that, px is actually a function, and you know what it means, that pxi, this identity operator, and we multiply the px to that function. That's the operator here. Rather than writing a px, I wrote it like this, pxi, because if you write dpx, period, it seems like we're going to differentiate px. But what this one really is, the first operator is here, and the second operator is here. The first operator is given the function y, we're going to multiply the px. Then we're differentiating. Think about the difference between d and px written there versus dpxi. So that's an operator. It's different. Answer to this operator, d on operator, is a compound notation for an operator. If you juxtapose like that, the answer is p prime x, which is the function, multiplied to this operator. So this is simply multiplying p prime to input function y, that kind of operator. And d is a differential operator. After you differentiate it, you multiply px. That's this operator. And this operator has a different notation. It's the same thing as this one. So I want you to look at this one and see what's really happening. If there's anything like this and some familiar name from calculus, one variable calculus, that kind of summarizes what's happening in here. Give it 5 seconds to figure that out. Yes, it's called the product rule. So if you put y in there, it becomes px times yx. And how are you going to differentiate that? First function differentiated, yx here, not differentiated. This px is not differentiated, but yx is differentiated. So after you write that product rule and try to get rid of y and turn that into an operational notation, you might verify that this is true. So this is what happened to this one way to write this